Hello everybody, I'm Antonella Galizia, researcher from CIMA Foundation and IMATI CNR, and I'm here to discuss with you some of the challenges we face during the years in weather and forecasting computation. And in particular, we will land on the solution that we are experimenting during the EVEREST project. In particular, you know that the EVEREST project has three validators, let's say, industrial validator of the technologies and the design environment, development environment we are designing and developing, sorry, for the rewarding. And the validators are three industrial applications, in particular, as you can see in the slide, and in particular, they relates to renewable energy prediction, air quality monitoring, and traffic modeling. So, as you can see, none of them relates with weather forecasting, but it is not true in the sense that both renewable energy prediction and air quality monitoring are actually based on weather predictions as the first step of their evolution, of their algorithm actually. So, and that's why we decided to present in this set of seminars also the weather prediction as a standalone software component, because let me say, apart from these two applications, also traffic modeling could benefit from weather data, weather prediction data. And this could be, and not only it can benefit, but it can include also this kind of data in its path. And this is a general vision that we can find. I consider this very nice cartoon that has been developed by the World Meteorological Organization, WMO, where they explains why the world needs meteorologists and hydrologists. So, because you see here that here we have all the core is about weather monitoring and climate monitoring, but at the end there are a lot of applications that can benefit, that are using such kind of data, from agriculture to aviation, shipping, pollution control, transport, international cooperation, and so on, environmental protection, and so on and so forth. So not only meteorologists and hydrologists, but also mathematicians, computer science, engineering, because as we can see, as I was mentioning, taking into account this very nice cartoon, many application benefits or are based on the weather prediction. And weather prediction has always been a great challenge for society that poses a lot of technological issues. Nowadays, we are not more involved, or the actual focus is about climate change, but this is another story. While the point about weather forecasting is that the weather prediction, I would not go too much in deep on that, but weather prediction has always been faced with a deterministic approach, so the resolution of partial differential equations, but there is also a very chaotic nature in this kind of computation. So apart from that, we can always say that weather prediction has always been considered as a highly demanding application for APC facilities, both in terms of storage and computational power. So And now again, I explain what I was saying on the first or the second slide. I mean the fact that both energy production and air quality prediction can be considered as a weather-based application. And in fact, we found some mention of this kind of application into the cartoon of WMO. And as I was saying, they represent first logical steps and software components of such applications. And while developing such application, while improving energy production and air quality predictions, we saw that both in terms of accuracy and computational aspect, the main driver is the weather forecast. So what I mean is that most of the time is consumed by weather forecasting, as well as the accuracy. The better the accuracy of the forecast impacts highly on the accuracy of the prediction. So better forecast prediction, better energy production prediction. So inside the EVEREST project, we are considering the WRF model, so the weather research forecasting model, that is a state-of-the-art numerical prediction model that propose physical schema, numerical and dynamical option, initialization routines, and also what is called data simulation packages. And it is actually a community-based model. It means that we have more than about, let's say, 50,000 of registered users up to 160 community country, using it on over 160 countries, so a very worldwide community. So let's give some insight about meteorology. Weather forecast means actually the study of the state of the atmosphere, not only the state of the atmosphere, but of its evolution in time. And so we probably never focus our attention on that, but the atmosphere is a fluid, and thus it is modeled by fluid dynamic and thermodynamic equations, and many other physical laws. I will give some very brief insight in few seconds. Actually, the equation that are at the base of weather prediction are the Navier-Stokes equation, and everything they lead, because we know that they are very difficult to be solved, and they, just as a curiosity, the solution of Navier-Stokes equation has been proposed as one of the millennial problems that has been launched by Clay Mathematics Institute of Cambridge in Massachusetts, and the first scientist that could solve this problem will win $1 million. So this is actually one of the 8 most important problem in science. With all this means, of course, because it is very difficult. And why this is so difficult, at least in terms of weather forecast? Because the model has to model many physical laws. So it has to consider all the radiation equation, so the fact that the sun hits the ground gives back this heat in the air, and the air can create some convection. And here we have the water cycle. So the idea that as soon as it is raining, the rains go down to the floor, to the ground, and it can be drained by the ground, or if it impacts in some river, the liquid water turns back and goes in the sea. That again will heat the air, that can somehow create convection if it is the situation, of course. And so the snows and the water and the rains and so on and so forth. And so the water cycle, apart from the radiation equilibrium, has to be respected. So what I would say is that there are a lot of physical phenomena that are very well known in our educational study, but they are easily modeled into equilibrium law, fluid dynamic, thermodynamic, and this kind of equations, but the resolution of such equation can be not easy and can create a lot of instability. And we are talking about, and also we talk about, when we talk about the fact that clouds can be created, please let's consider that there are many different kind of clouds that can be distributed in the atmosphere, and they have different impact on the radiation itself. So it is even more complex on what we are considering. Take here the idea that we are not, of course, working on all the atmosphere, but only in the lower states of the atmosphere. So this is the flux formulas from Eulero equations, and we could talk about many kind of resolution of this law, but this is not what is of interest for us. But again, I want just to underline that this is a very complex resolution of equations, and such equation can create some instability. So what we do is for sure to discretize our domain, and since it is a geographical domain, here I reported an example of how this can be done. Here we see that since we are discretizing a volume, we have different voxels. Here we consider them more or less of the same granularity, of the same size. Please let's take into account that when we talk about forecasting modeling, weather forecasting modeling, we have a grid space, that is what I'm showing here on the globe. We are actually considering such nice pictures considers the globe, and so it is a global modeling, while usually with weather you can have also local model for the forecasting. And but you have, and here we are seeing that we have different voxels, that we have different vertical column, and we have to consider the exchange that we have among each voxel in a vertical volume, but we also have to consider the fact that we have some data exchange also on the horizontal direction. And going back to our very complex equations to solve, here we can see that usually it is distinguished among the variables that are considered and calculated at the surface, and the ones that are instead calculating in the column that of course are atmospheric. And again, this is not easy. But as I was saying, we have also the fact that we are talking about modeling, weather forecasting modeling, so not only the state of the atmosphere, but also the evolution. So apart from the step, the geographical grid step, the space, we also have the time steps and take into account that they influence each other in the sense that in order to ensure a bit more of stability, we need to correlate such data. 10-20 kilometers for each voxel is a nice granularity if we consider actually the entire globe, but now we have nowadays 10 more than 20 is a very nice time, geographical step for our computation. And let's add another bit of difficulties, considering that such vertical volumes, of course, will be very considers not only the surface, but when we are talking about the surface, let's analyze a voxel, sorry. We have the vertical layers that we are considering, but we need to consider that the surface is not regular and is not always of the same material. What I would say is that when we are considering the grid spaces, we are considering such kind of boxes, but we have never forget that we have also to model the ground itself. So the idea of having a nice description of the orography of the geographical area in order to actually understand which are the possibility, because of course to have mountains or hills will be different from having plain surface. To have sea or rivers will be different with respect to having buildings or green areas, and this will impact actually everything. And so here we understand which are that it is important to have an high resolution to actually have a nice description of the feature of the geographical area. Of course, we need to have coordinate systems, but we have to also take into account of many physical phenomena that happens in a, let's say, on a smaller scales. For example, the water cycle and so on and so forth. If we have very high resolution in terms of grid spacing can be lost. And so that kind of phenomena has been introduced as parametrization schema, just to actually keep the feature of the actual grounds from the orography. And again, this is the differences that we can have, of course, considering these different kind of resolutions. Here we can see that somehow hills and mountains can be distinguished, while here not. And this is why in the last decades, the weather forecasting improved a lot, because as soon as we want to improve our prediction, and particularly here I talk about extreme events because Imadi and CIMA studied a lot on this topic, spent many effort on that, and what we found was that a very fine resolution in space and time can improve the forecasting, but improving grid space and time steps of the forecasting requires for a lot of computational power, notable memory and computing itself. So the higher the better, but the higher it's also the more requiring, and the required for resource can not always be satisfied, managed by all meteorologists. Another point on which that allowed a great improvement of the predictability obtained in the last 10 years, in the last decades, from meteorological forecasting prediction relates the data observation. And it has a physically based reason, because we were saying that what we have to solve are a set of equations, partial differential equation, and we know that when we talk about differential equation, what is important is the initial state and the boundary condition that we usually set while solving to solve our equation. And here, which is the idea that the initial condition is nothing but our atmosphere, the atmosphere. So what we need to have is an high quality description of the atmosphere. That's why I put on this angle this picture from, again, WMO, that depicts different and very heterogeneous kind of data sources. Goes from satellite, balloons, in situ, sensors, radar data, data from sea or from the river, data that we are able to achieve thanks to airplanes, and many other sources. So the idea is to use all this data to represent the atmosphere, and then use such data to represent, to provide the initial and the boundary condition of our model. It will be even more complex, of course, but let's do in this way. Up to now, what is done, or what was done, was to consider another model that simulates the atmosphere. So one usually use a global model forecasting, while now the idea is to use such observation to let them to be assimilated in the model, so to feed the model. But please, we have to take into account that we give as an input the observation, but also all the errors that derives from observation, that are not only errors due to the data source itself, so from an engineer perspective, but also from the fact that we don't have observations that are homogeneous in time and space. There is a lot of, although now more and more data are available and open, but it is not so easy to use the data, observational data, for the assimilation. So the idea is exactly this one. Here at the ACNWF, at this link, you find a very nice videos that explains in deep how observation are used for data simulation and to force somehow the model, thus to improve the predictability. The idea is, if here I start my prediction, what they do, and in general the idea is to consider, to use the observation of at least the last 30 minutes, actually At CIMA Foundation, we consider 3 hours, and in the Everett project, we consider 3 hours, 2 cycles of 3 hours actually, so 6 hours. Where you start, you consider the data, you have the observation you have, and you start an algorithm that combines them, thus to provide your initial condition and to be used as input of your model. And here with this slide, I would introduce again more cows, actually citing again what I just mentioned in the first slide, where I said that there is an intrinsic chaotic nature of the phenomenon description. So I could just remind you that the Lorentz skies theory and the very famous butterfly effect was born actually with meteorology, in the sense that there is a very nice story that talks about that analyzing, having again the same run, the same simulation for the prediction of a meteorological forecast, the results were very, very different. And that's how the butterfly effect was born. So the idea is related to instability, the fact that the atmosphere is partially chaotic, and although it is a deterministic, in the sense that the evolution depends is on the past, but it is also very difficult to predict because it is very, very sensitive to the initial condition. So the first one, again, has been Lorentz and all the nice stories. So, which is the actual way to avoid such butterfly effect? Is the idea is to have different run where we introduce a bit of noisy in the initial run, in the initial condition, to see where and how the different prediction diverges. And the idea is to have the so-called spaghetti plot, where we are moving from a deterministic to a statistical approach, where the idea is this time to consider the part of this is the statistical that we can engage, that we can derive from our ensemble approach, and we can see that the higher probability is in this interval. But it is just to give an example, a comprehensive example of what happened. And just to understand how these spaghetti plots are used, here you can see two simulation we had from the ACNWF for two different events. One occurred in June 1995 and one occurred in June 1994, I suppose. And here we can see that we have two different, actually different plots. Here we see that the spaghetti plot has a very common direction, where here they are going in a disruptive way, let's say. So this is a trustable forecasting, while here we can say that only on the first days, here in the first days, it is actually nicely gone, while here we can see that after 1 or 2 days of simulation, it is very hard to predict the air temperature. So a further simulation more close to these days has to be considered. Again, while growing taking into account a very, very complex model that has to discretize many, many factors, and I would simply leave this as a memory of everything we said. We can see as soon as the computer power growth that model resolution improved. But a very nice approach that considering also data simulations, another way to try to reduce the uncertainty, so try to improve, to increase the predictability of the model, is the running of ensembles of simulation of forecast, thus to have some more trustable information. And both the direction, I mean, improve the granularity, but also data simulation, so the use of much observations to improve the description of the atmosphere at the initial state of our condition of our model, and to go for an ensemble prediction is actually what, in terms of work, the Everest design environment can support such kind of computation. So the idea is to improve the accuracy of the weather prediction, of course, mainly following two directions. From one side, to push further data simulation, considering more and more observational data sets, so more and more data sources that we can trust and ingest through data simulation cycles in our model, in our prediction. But on the other hand, what we would have is also to improve the speed up performance figure by using the FPGA hardware, so by exploiting the accelerators that the project is providing to implement and test an ensemble prediction. Again, all this can be used then to produce meteorological scenarios that can feed weather-based applications as the ones used in the Everest use case, as the ones of the Everest use case. In order to do that, of course, other tools, for example, for complex workflow management, would be very beneficial and appears as another point when the Everest project could support this kind of applications. So the idea is very, very simple, at least in a theoretical way, phase. We have our source code and a model that has to run on an APC platform. We want to go, of course, we have some configuration parameter that is mainly related with the physical applications, with the meteorological forecasting we are doing, but of course there'll be also some hardware parameter, and compilers and dependencies will close the loop, and thus the model can be run. And the idea is to consider some hybrid and accelerated hardware to run the WRF model. So the idea is to consider not only CPU application, but also CPU hardware, but also accelerated heterogeneous infrastructure as FPGAs or GPUs, where I would avoid to enter in the technicalities of this work, but and so the idea is to actually understand how to enable the run of the a WRF model not only on general purpose hardware, so general high performance computing clusters. That is what we are able to do also without the EVEREST project, but also to consider which kind of software stack we need in order to go and to on accelerated hardware that can improve the execution time of the algorithm. And so the idea is here, more or less, where we replace with kernels with SDL snippets. So we have that our code, WRF code with stubs, can be somehow considered forked, and we have the binary files that are compiled through Intel CC, and we are able to go on high performance computing resources, homogeneous, let's say standard high performance computing clusters, while thanks to DSL and this time exploiting a DSL compiler, we have the possibility to have HDL, so kernel representation, that are able to be executed both on high PC, but the actual goal is to go on FPGAs, at least in this. And so the path we followed, the strategy we are following, analyze the WRF model firstly in terms of performance. And what we did was the profiling of the application in terms of execution time and resource consumption, sorry. And so what we did was the analysis of the code in order to point out, to individuate which are the most compute intensive module that can be transformed in kernels to have to be offload to the FPGAs, and then a possible strategy to offload that part of code on the FPGA. What we discovered that the most consuming part is the radiation part, the radiation driver. The radiation is the physically based. Here I comment before this is this part. So the idea that I already explained, that the radiation scheme provide atmospheric heating due to the radiative flux divergence and surface downward long wave and short wave radiation for the grounded budget. So what it means? That as soon as we have our heating of the surface is heating the air, and as I said at the beginning, this is very different, very complex to individuate. And we have different, again, you see the subscale orographic drag. So again, we have to remember that the orography is very important. And here we have the turbulence diffusion that are very sensitive to heat flux. Okay, and again, if it is cloudy, this part will take more time because of the reflection also from this point of view, the divergence actually. And so it is a very complex module, and again, its time execution depends on the kind of on the situation of the atmosphere. Okay, but more or less this is the most intensive part for the WRF model. And it is usually so intense that it is usually so expensive that it is not activated every cycle, every time step, every cycle of calculation, because it is very expensive, but also on samples on with a specific frequency. And this is a very simple more or less representation of the goals that are only considered in the radiation module, the RRTM module. And so just to make us understand how it can be complex and not simple. So now let's discuss very briefly a possible strategy to offload such part of computation on FPGAs. The road that we are following is a two-step strategy, where we firstly need to re-engineer our code to have a more flexible and modern RRTM module, so the radiation module, and then offload such RRTM execution on FPGA resources. We are now in this phase of testing the stability of the new implementation that we found. It is here we found a very nice paper talking about that, that provides us very promising ideas and to be used on this to have this approach also in the WRF kernel, in the WRF model, sorry. And so the idea is exactly this one, to offload such part from to see how this piece of code that has a very high data volume can be offloaded, can be executed without inserting, of course, instability to the code. And this is where we are and what we are testing. So if you look here, the idea is to, so the idea is to have this part of the computation, so what is called the WPS, so the word preprocessing system. Let prepare the initial the input data, then that has to be used for the run of the work model. Then here we start the execution of the data simulation algorithm, taking many others observational data, and then up to now we are going on this way, on this way, sorry, the execution of the application itself on simple high performance computing, simple in the sense of standard. While now the idea is to enable it on FPGA's execution. And that's the strategy we are applying on to achieve the goal that we would have in the EVEREST project, but more in general, this is one of the approach of meteorological forecasting systems. Thank you so much, and goodbye.